This is Team 31's Project 3 presentation, where a Gears robot was designed, developed, and demoed, where the presentation will report on the findings. To give a brief introduction to the problem, natural disasters happen all across the world that affect multiple developing countries and their economies, obstructing further development. Team 31 was tasked with developing a Gears robot that could navigate through a maze and avoid hazards, develop a map that shows the path it took to reach the end and also the location of the hazards, and deliver a cargo container at the end of the maze. The project management component for the physical components of the design were developed using a functional block diagram and also a work breakdown structure. The work breakdown structure contained the main portions such as the navigation system, the cargo storage, release, and transportation system, the Raspberry Pi module system, drivetrain, and also the software component. In the functional block diagram, it contained how the individual components that were mentioned in the work breakdown structure would connect with other components and also the user. Project goals were also developed by Team 31, which connected the main components mentioned in the last slide and gave them quantitative values to look forward to when testing and in the final demo. The last part of project management was creating a timeline. A timeline was created from March to end of April, and each week had a major goal to be tasked with. The team met 1 to 2 times a week, and for each meeting, a goal was specified before the meeting started to signify when the team should end meeting, and also what the goal for the day is. Next is the design making process.
Early on, the team had 2 very basic designs that had general but different ideas. The designs were simple, so they had many similarities, however, there were areas with differences. For example, Design 1 used 4 wheels, all on a drivetrain, while Design 2 had 2 wheels and 2 sleds. Additionally, there was a difference in front versus rear loaded cargo between the 2 designs. Another small difference was in the mounting of the IR sensor, as can be seen in row 4 of the table. The final and maybe the biggest difference was in the measurements of turn, with Design 1 using motor power and position, and Design 2 using the gyroscope. Using these designs, the team created a decision matrix to determine which design would be pursued throughout the project. As you can see in the chart, Design 2 ended up having a higher score, meaning this was chosen for the gears. The biggest separating factor was the ease of coding, as the 4-wheel drivetrain and the direction calibration will be much harder to code for Design 1.
The gears can be divided into 3 main mechanical components: the chassis, the cargo drop-off system, and the sensors. The drivetrain consists of 2 wheels in the center of the gears. Team 31 decided to only use 2 wheels so that only 2 motors were necessary. Additionally, Team 31 positioned the wheels in the center of the gears so that it could pivot instead of turning on a radius. This was to accommodate for the narrow hallways. Moving on, the chassis can be broken down into 3 main sections. The front half of the gears mostly consisted of a platform for the cargo drop-off. The back half was like a cage used to house the Pi system and the battery. Finally, the rear of the gears had a sled to support the weight of the Pi system and the battery. Team 31 decided to use a sled made up of 2 Lego pieces instead of wheels to reduce friction. Moving on, the second main mechanical component is the cargo drop-off system. The cargo sat on top of a platform in the front of the gears. Team 31 decided on a front-facing drop-off because in a real-life situation, the gears could drop off the cargo and back up. If the cargo were in the rear, the gears would have to turn around and navigate around the cargo that was dropped on the floor. To push the cargo off the platform, Team 31 used a vertical motor with an arm. The arm rotated 90 degrees on the XY plane, assuming that Z is up. While testing, Team 31 noticed that the cargo would flip over when pushed off the platform around 2 out of 5 times. To preserve the orientation of the cargo, Team 31 added a ramp that flipped over when the cargo deployed. The ramp also acted as a gate to keep the cargo still while the gears was in motion. The third main mechanical component are the sensors and their mounts. Team 31 needed to use an IR sensor to detect the IR towers. Team 31 decided to attach the IR sensor to the ramp. This allowed the IR sensor to be at the front of the gears without obstructing the front ultrasonic sensor's line of sight. Moving on, the IMU sensor was attached underneath this cargo platform in the middle of the gears. Team 31 did not prioritize the placement of the sensor, so this was a good place did not impede the other sensors. Another sensor that Team 31 used was the LEGO gyroscope sensor. This needed to be placed in the center of the gears. More specifically, this needed to be placed in line with the wheels so that the turning data was accurate. Team 31 decided that the best place for the sensor was in between the drop-off arm and the pike gauge. Also, Team 31 placed the gyroscope so that it was collinear with the two wheels. Finally, Team 31 used 3 ultrasonic sensors. One LEGO sensor was placed underneath the cargo platform adjacent to the IMU sensor. Team 31 positioned this ultrasonic sensor in front of all other sensors to assure that its line of sight would not be hindered. Team 31 also used 2 Raspberry ultrasonic sensors. These were placed in the center of the gears above the wheels. Team 31 created a mount out of Legos for one of the Raspberry ultrasonic sensors and a 3D printed mount for the other. This concludes the mechanical components of the gears.
This is Team 31's software logic and general programming approach to Project 3. As the code was being developed, it was known what sort of tasks needed to be done. These were broken into functions. To quickly grasp the relationship between functions, this function map was created. It served much like a functional block diagram for software functions, showing both a function's purpose and relationship to other functions. Blue functions primarily gather and process data through sensors. Green functions primarily accept, process, and execute movement instructions. And red functions accept, process, and output data. It's possible for a function, navigate for example, to fall into 2 of these categories, so it receives an intermediate color. Vertically, functions are arranged into 4 levels: main, FL1, FL2, and FL3, with FL standing for function level. Main simply contains a single program used to organize and execute lower level functions, and any function in a given level can call a function in a level below, but it should not call a function in an upper level. The main program is essentially a simple loop. A high-level flowchart is shown here, and it can be seen that while the gear system is running, sensor results and navigate are being called over and over again, waiting for the indication to stop. This stop comes from sensor results and only occurs when gears is ready to drop off the cargo. When the command is issued, the main loop stops, the cargo drop-off function is called, maps and tables generated, then the gear system reverses away from the cargo to indicate the cargo is dropped off and it is safe to retrieve. Main also serves as the top-level data storage mechanism. Data is passed from main to other functions, and from those functions to even lower-level functions. Data is then returned from those low-level functions up through to main, where it is stored. The 2 primary data lists are map data and intersection list, used for mapping and intersection purposes respectively. The purposes of each element will be discussed later, but it is useful to note that they are stored in main. Sensor results is the first function to be discussed in FL1. The detailed flowchart is provided, but the key aspects are dead-end recognition, intersection navigation, and hallway navigation. Data is collected from all 3 ultrasonic sensors, the IR sensor and the IMU magnetometer, and then it is analyzed to determine whether to go straight or which direction to turn. The first if statement checks to see if all ultrasonic sensors reach sufficiently high distances, indicating gears is in the open. If so, the string stop is returned to indicate a stop for the cargo drop-off. Otherwise, it continues to the next if statement. Essentially, this next if statement is looking to see if at least 2 of the ultrasonic sensors indicate open hallways in their directions. If so, intersection navigation is entered, and that will be discussed in a moment. If gears is not in an intersection, it checks to see if there are any barriers or hazards to its front. If so, it returns the letter F to indicate forward movement. If not, it checks the left side is clear, and if so, it returns the letter L to indicate a left turn. If neither the front nor the side are open, it checks the right side, and if it is open, returns the letter R. And if none of these are open, it turns around. Now for the intersection navigation, essentially it looks at this intersection list, and it checks these possible headings. Possible headings is updated every time it's in the intersection to see which headings are an option, and then there's also headings used, and these headings used are the headings that the gears has actually gone down. Essentially, it goes through this list and checks to see if it has gone down the front heading, and if not, it goes front, then it turns left if it's possible, and then turns right if it's not possible to do that, and then finally it can turn around as well. That is the sensor results section, and these returning values are returned back to main, where it is passed on to navigate. Now, navigation checks to see which value has been given, and then based on that, checks to see which way it can turn. So it either pivots or goes forward. There's also the mapping function here. The mapping basically iterates through the map data here, the map data list, and checks to see the coordinates, the heading, and the hazards, especially the coordinates in the heading. It will iterate through, change the units to the correct units, round them, make a list of all the points it's actually been down, and then goes through all the possible points and prints 1, 2, 3, or 4, or 5 based on which points it's actually been on. If it has been on that point, it prints one of those options, and if it's not been on that point, it prints a 0. There's also the table output, which is similar, except for it just checks the actual hazards, and if it has hit a hazard, it will print the applicable data and the data type. Finally, there's software logic for straight navigation, cargo drop-off, straight distance, and pivots. These rely heavily on PID control. The PID parameters are passed back and forth from these functions, from navigate and back to these functions over and over again in a loop. The PID parameters were chosen based on the speed at which the gear system was allowed to move and how much it was oscillating back and forth. There's also an angle limiter for the straight navigation so that it won't turn too far off of the straight navigation path. Cargo drop-off just activates the small motor for the cargo. Finally, there's FL3, which uses the drivetrain function, and this function will use differential power to calculate an applicable motor power data values for each motor, both the left and the right.
In order to get the sensor values that would stop the robot from hazards, the team used the code and procedure from the in-class lab to collect the data on the magnet strength using the IMU. It was known that the magnet had a no-entry circle of 5 inches during the demonstration. As can be seen in the graph on the right, 5 inches corresponds to a value of 397, and 6 inches corresponds to a value of 288. So the cutoff value was initially set at 300. However, when testing, the team realized that the gear system was getting too close to this and breaching the no-entry circle. It was then discovered that the IMU sensor was 2 inches from the front of the vehicle. This meant that new critical values were needed and are shown in the graph on the next slide. With this new knowledge, the cutoff value for the magnetic beacon was then set at 200 instead of the original 300. The IMU sensor values were chosen in a very similar manner. Values were recorded by setting the robot a specific distance from the LED tower and writing down the values. The IMU tower had a no-entry circle of 4 inches. With this data in mind, the team made a graph with critical points at 4 and 5. Based on this data, a value of 100 was chosen as the cutoff value for the IMU sensor. No additional adjustments were needed to this value since the IR sensor was mounted on the front of the vehicle.
These are the initial designs the team made for the 4 types of cargo that would be carried: for medical supplies, food and water, fuel, and emergency shelter. After creating these logos, the testing was done to see the effectiveness of 4 designs. The designs were placed on imaginary crates on the photos displayed on the slide, and a Google form was sent out gathering data on what the audience thought were inside those crates, as well as adding for feedback once they were notified of what the contents were actually meant to be. And the team took the average, with the medical supplies having 1.232, food and water 1.304, fuel 2.333, and emergency shelter 1.826. And then using the feedback, the team created a few further changes to make it more effective and more responsive to a greater audience. The logo designs after the main changes were made to the fuel and the food and water, where the fuel, the canister was enlarged to put more emphasis on that component, and the apple was placed to make another example to make more emphasis on the food and water component.
Team 31 overall had a very successful demonstration. However, at the end, Team 31 was able to analyze the positives and the negatives of the prototype design. The gears produced, the positives are as follows. The gears produced an accurate map of the path taken. The gears avoided all walls except one. The gears detected all hazards and navigated around them. Ultimately, the gears navigated the maze almost perfectly. The only problem Team 31 had was the final right turn to exit the maze. This failed turn was mainly due to 2 reasons. The first being an inaccurate gyroscope sensor. As the gears continued to navigate the maze, its idea of true north started to diverge. The margin of error started to build up as the gears continued to make turns. And at the final turn, the gears did not have a good reading of true north. The second reason that the gears failed at the final turn was due to the motors. Team 31 had designed the code to where the motor power was the main dependent variable. However, due to slight differences in friction and in the motors themselves, the wheel speeds differed even though the motor power was set the same. Team 31 tried to account for this difference by using the gyroscope to keep the gears centered. However, this was not enough. In the future, Team 31 would like to control the motor position instead of the motor speed so that the wheels spin at exactly the same speed. This would prevent veering off a straight line path. Additionally, Team 31 needs to revise their final code. Due to time constraints, small mistakes went unnoticed. For example, the gears did not map the hazards, and this was because Team 31 had a typo in the code. However, with more time, Team 31 suspects small mistakes like this would be easily ironed out. Finally, Team 31 realized that the sled on the rear of the gears would not be viable in a real-life situation. The gears would not be able to navigate obstacles on the ground with the sled. If this were to be scaled up, Team 31 would need to change this portion of the gears design. Overall, Team 31's prototype met almost all requirements and requires only a few slight improvements.
This slide shows the output map from the team's design. As you can notice, it mapped correctly, except for the hazards are not listed in the map. And then the video on the left is actually an IR camera that the team had mounted to their robot. So it really gives a cool perspective on the robot's point of view and the IR beacon, which is not visible to human light. Thanks for watching our presentation.